Thanks for the invitation and the chance to talk in an awesome space. I'll try to keep your attention on the wall and not the view. So the talk is in two parts. I want to talk first about perhaps a sort of understudied area in machine learning, which is getting the maximum performance from single machines. Understanding what the limits are and designing right to those limits. And we use a method called Roofline Design that we've stolen from computer architecture. And the second part of the talk is going to be about taking those fully accelerated single node algorithms and scaling them up so we can get, hopefully a couple more orders of magnitude of performance out. And that's still a version of Roofline Design, and I'll try to make the connection, even though these look like very different tasks, I'll make a connection between them. So as well as being a faculty member at Berkeley, I've actually spent a lot of time in industry, my summer jobs. I've had several industry leaves in the last decade. So I've been at companies doing analytics for about 40% of the last 10 years. And I tend to work in production teams, not in research, because depending on the company, there may or may not be actually much production consequences from the research that happens. But I worked on two systems at Yahoo about a decade ago. We did a production recommender at eBay, and I've since been at Quantcast, Microsoft, and recently Yahoo. Most recently Yahoo again. And so it's been a real sort of lesson in deployment and challenges. And I'm just going to quickly sketch sort of three priorities that have come out of that experience. So this is a simplified picture of data scientists' workflow. And I'm collapsing a lot of the complexity that Steve just talked about into this first circle, which includes wrangling featureization, transformations, the front end sort of query processing that leads into machine learning. But I still would argue that it's important for that to be a tightly coupled loop. Basically, hypotheses in data science are really hypotheses about structures in the data. In order to test them, you actually have to typically build a model and try it out, evaluate it, and I would argue actually tweak or actually customize the model. I'm not sure that happens enough, but I think it's very important to be able to do that. And the other challenge is in taking prototype models into production with integrity. By that I mean that the models that are done as prototypes are often in a prototyping language like scikit-learn or even R maybe. They're not suitable to be translated directly. There's efforts along those lines, but usually there's a complete refactoring of the code when it goes into production. Often refactoring is a good thing. For machine learning, it tends to be a bad thing because it's often done by a group without machine learning expertise. It's done in a completely different environment. There are shortcuts taken, and in virtually every environment I've worked in, there's been a significant loss of performance in that translation that nobody really noticed. In order to notice it, you have to actually pull back data and reanalyze it and validate the online models. It's not really part of the normal testing that companies do. People easily explain that away also, that the production environment's different from the prototype environment, and it's harder, and therefore the performance is not as good. If you do a correct offline training and modeling, you should actually always see almost always see an improvement in performance. And I've spent a fair amount of time tracking down the translation process and trying to iron out the kinks, and usually there's some big gains if you do that. Anyway, but what I want to argue in the talk is that we could really improve that process by basically developing tools and languages that allow a direct translation of the same code into production. And the last point I'm going to emphasize is this customization idea. I already mentioned this idea that if possible, people should be thinking more about actually changing models, not taking machine learning models and treating them as black boxes, but changing the loss functions, the secondary constraints, and so on, so that the model is really solving the problem that you want to solve, not what the black box is solving. So those are three goals in the work that we've been doing. And I feel that there's enough weaknesses in the other systems that I've used that it was worth going off and building a completely new toolkit to address these issues. And one issue is performance. So if you've been tracking graphics processors over the last decade or so, they've always been very fast at dense arithmetic, matrix multiply and so on. Very good for scientific computing, but not as good for typical machine learning on sparse data, text, or web data. But that's actually changed in the last few years, primarily because of the very fast memory that GPUs have acquired. And in fact, now they're significantly outperforming CPUs on sparse data problems, the ones that we care about most. And they're continuing to pull away. So that drove me, primarily that was the thing that drove me, well, I really need to do something about this. And the other thing is that there's a very nice, I guess, what's the word, a preeminence of mini-batch methods. Stochastic gradient has become sort of a real workhorse of choice for big data processing. And it's extremely compatible with graphics processors. You can park very non-trivial models in the graphics processor memory, and you just need to send little mini batches of data into the graphics processor to train models. So first thing is performance, getting the maximum performance from the hardware that we have today. And the gaps are, as I'll try to convince you, are bigger than people have thought. The second thing is the customizability bullet. So I've always gotten a lot of value out of somehow taking standard models and tweaking them to actually fit the application. And I think maybe more people would if it was easier to do. It's currently pretty challenging to do that. And the last bullet is we'd like to, first of all, be able to explore very quickly, try ideas out instantly, run multiple concurrent parameter sets, do parameter gridding and so on to very quickly optimize models. But then take an optimized model and run it with its exactly as designed in the prototype, run it in production. Okay, which involves typically, or sometimes at least, scaling up on clusters. All right, so those were the goals and the approaches that we take. First of all, for performance, we use Roofline Design, which involves explicitly articulating the performance limits of CPUs or graphics processors. We build the high-level machine learning toolkit on top of a matrix layer, like many other toolkits do this as well. Ours, though, completely hides the identity of the matrices as graphics or CPU matrices. And surprisingly, other toolkits really don't do this, as far as I'm aware. MATLAB's sort of done it really quite poorly. And this is really a prerequisite, because given that the graphics processor is sort of the dominant machine learning or the dominant computing engine these days, it's very important that it be basically transparent. It's easy to use as a CPU. And for customizability, we built this toolkit with reusable components. So you can substitute a basic loss function that really defines the model, an optimizer, a stochastic gradient or LBFGS or something, and then various secondary criteria which include regularizers and so on. So you can plug all those, mix and match those things, and even, because they're quite simple themselves, clone them and create your own custom version. And then for exploration and deployment, we wanted an interactive, scriptable, somewhat graphical environment, not in the style that Steve described. It's still a text prompt, but we have various graphical modules that we can bring in, and we're trying to extend that. We are trying to add a significant sort of graphical interface for model customization, which basically allows you to dynamically trade off secondary loss functions against the primary likelihood function. And so there is a sort of a vision and a PhD thesis around interactive machine learning that we have. And for deployment, it's extremely advantageous to work on the JVM, so you can coexist with Spark and Hadoop and so on. But for performance, you want that low-level CUDA/C optimized code level. So we integrate native code with the Java high level, Java/Scala high level. So we can, I would argue you can have sort of your cake and eat it too. You can get extreme productivity like Python, but still have full performance and clusterability. All right, so let's get into some of the details of roofline design specifically for single machines. So roofline is a term coined by some Berkeley PhDs and David Patterson a few years ago. And the idea is to articulate basically a set of linear constraints. When you take a conjunction of linear constraints, you get some kind of convex shape, and typically looks like a roof. So for a processor, you typically have a fundamental ALU limit, which is how many arithmetic operations you can do in a second. Those are flat lines that give you basically constant throughput. Along the x-axis is sort of roughly a density measure. It's how many times you operate on each datum that you're reading in from memory. So then it's in flops per byte. So if you do one flop on a datum that's 4 bytes long, you get a quarter on that axis. Now, when you have memory, various memory modules, memory has latency. And the latency determines how fast you can read data in, because you pay a constant penalty. So you get lower throughput data that you're not going to use. So that gives you these diagonal lines. This is just for a graphics processor, but you can see that it has a very wide range of memory performance. And let's see, do I have, okay, I'll get to the memory in a second. I'll just point out the most obvious difference between graphics processors and CPUs is that the graphics processor really is mostly a processor. A CPU is mostly a cache. And the loads that CPUs are really built to deal with involve a lot of sort of data movement, data reorganization, less computation. One reason that CPUs are perhaps, I would argue, a little bit less suited to big data is that if you have very big models or big trees or big hash tables, you're basically losing the value of the caches because they're too big to fit into cache. And basically you're really only benefiting from the computation piece of the device. And we see that, and actually it's quite interesting to look at the solutions that we came up with as workarounds to get high performance with very large data structures, but they're quite different from what you traditionally do on a CPU. Anyway, so one difference is the arithmetic performance. The second really big difference, perhaps even in some ways more surprising, is a difference in memory performance. So first of all, the memory on a graphics processor is very fast, and they're using a variety of clever techniques to make it faster. I'm picking a somewhat mid-range PC here, not a super high-end server, because the graphics processor does that I can get for about $500. I can spend much more and use more energy on a CPU, but this is roughly normalized for cost. And another big difference that I'll get to a bit later is that there's an amazing abundance of register storage, which runs at full speed, runs at single cycle operations on a graphics processor. CPUs, by comparison, have a minuscule amount of memory. When you're able to site your computation in registers, you can go at the full speed of the machine. And there's some really interesting new use cases for that we've been exploring. And it really isn't possible to do that. There's a large number of things that you can do in that much space that you just can't do in that much space. Okay, so first thing is matrix kernels. Given that we know the roofline for ALU and also main memory, when you have a big matrix to multiply, it's going to have to come through main memory. The caches won't help you very much. But if it's a dense matrix multiply, you end up using each element many times. It's being multiplied against a row or column of elements of the other matrix. So you have high reuse, and so you actually don't have to worry about memory for dense operations. So GPUs just end up being faster because there's more ALU there. In the sparse case, like if you're doing logistic regression, you're doing basically a big sparse matrix of data multiplied by a model vector. And you actually there also have a big advantage for a GPU because of that main memory difference. And so as long as you have a primitive that's fully rooflined, you can get that performance. Now, interestingly enough, we've actually found that NVIDIA's matrix libraries, the Q-sparse libraries, don't come close to the GPU roofline for most common machine learning type data, because at least not right now, as of about 2 weeks ago when I talked to them, they're aware of this problem. But like a lot of matrix libraries, they've been optimized for scientific computing, which typically has very uniformly structured sparse matrices. When you put typical text or web data into those kernels, they do very poorly. So this, where are we here? This rooflined sparse multiplier is something that we wrote. And we were sort of guided by the roofline. We basically evolved that algorithm till it was at the roofline because we knew it should go there. And that actually worked. And there's some sort of a few little tricks, mostly heuristic though. But it does actually make a huge difference simply being aware of what these roofline limits are. Because you basically know you can keep trying and probably you'll succeed to improve the kernel. So there's a little bit more to it than that because you can typically figure out where bottlenecks might be by using profiling tools. But anyway, so that gap gives us a really big advantage in machine learning algorithms that use our GPUs. All right, so here's the toolkit. In order to sort of support customizability I mentioned, we built a toolkit on top of that matrix layer that includes sort of core classes to make it simple to develop or customize models. It's in the Scala language, but basically there's a master class called a learner class which is responsible for pulling in mini batches of data, almost always mini batch oriented. It can come from memory or disk or directly across from an HDFS source. And we get very good performance actually even with single disks, certainly with SSD disks, but we use LZ4 compression, which some of you might know is a very high throughput compression. It basically allows you to pull data as fast as you can get it off disk. If it's highly compressed, it'll actually be many times the capacity of the disk. And so we regularly get a couple of gigabytes a second, which is the equivalent of a pretty well-tuned 100-node HDFS cluster just from one node. So you can get that fast stream, and then we can farm it out if you have multiple GPUs. And as I mentioned, there's a basic model class which is responsible for gradient or some other kind of incremental update. Then there's an optimizer, which could be a simple stochastic gradient, or often it's a normalized stochastic gradient like Adagrad. And then the slightly novel piece is this mix-in architecture where you can add any number of secondary performance criteria. And the standard ones are things like L1 and L2 regularization, but you can also add common secondary performance criteria like inter-cluster, cluster independence and intra-cluster similarity. Also cluster size similarity as mix-ins or secondary criteria. So that allows you to basically create a bespoke model. And as I mentioned, our goal, we're working on graphical interfaces to allow people to make those trade-offs while the model's training. And we think that's a good model for really pulling in business logic, any other secondary criteria that you might be worried about into the modeling phase, so it becomes part of understanding the data. Okay, so in a bit more detail, BIDMach is the matrix layer. As I mentioned, it's in Scala. And I like Scala a lot. That's very obvious from these talks. And it's really an ideal match for this task. And I've used a lot of programming languages and environments, and this is the first one I've liked for, I can't remember how long, since I was single and in grad school probably. So it's an interpreter, but it has a just-in-time compiler. It's actually very fast. It's the fastest, it's often competitive with C. A lot of other languages have said that, but this one actually is true. And it benefits from that 20,000 hours of Sun employees optimizing the compiler and the just-in-time runtime and so on. It's interpreted. You can run scripts as well. One reason Scala is sort of a unique language right now is that it's considered a domain-specific language. So it has a fully open syntax. You can take almost any string of Unicode characters, including all the exotic math symbols, and operators in the language. So a lot of other languages that have operator overloading only overload the built-in operators. So Scala you can actually make look like other languages like API. So you can pretty much by just defining these operators. And in particular, you can make mathematics look like math. You can have Hadamard products and other kinds of cool-looking products doing what they're supposed to do. You know, it coexists with a lot of the Java-based runtimes, which is very nice. And another thing that if you've ever used Scala, you can actually take any existing jar and it becomes interactive. You can invoke the methods directly from the command line. There's no container needed. So every piece of Java in the world, when you load the jar in Scala, becomes interactive. It's kind of amazing. So we just use a standard Java native interface to link to C code when we need performance. But a fair amount of the basic run-of-the-mill matrix code is just in Java because it's efficient enough. Memory is slower than a lot of instructions these days. So unless it's over on the right on that roofline curve, we don't need to code it in C. It's going to be the same speed in Scala. Scala has some very nice parallel code. This is a big difference from Python. It has parallel collections. It has a full actor framework built into the language. So it makes it quite elegant for doing concurrent programming. So one of the things we spent a lot of time on that's kind of mundane and tedious but important is that we developed a caching scheme in the context of mini batch updates where you're operating consistently on same size blocks of data that more or less looks like there's a garbage collector. Generally manages to reuse all of the storage that you use. So that allows us to run on the GPU platform without memory management and not running out of memory. So we run terabyte data sets. Java, because I'm doing a lot of work with the Cafe toolkit from Berkeley, which is a wonderful toolkit, but it has a humongous number of dependencies on different packages. And when you try to port that to a different platform, it's a ton of work. Because we use the JVM, we consciously, and native code, we consciously avoid system-dependent features in native code. We always use the Java virtual machine for that. So as a consequence, we distribute this as pre-built binaries that should run, as far as we have found, they always run on different versions of these platforms. And otherwise, it sort of feels like using MATLAB or SciPy. That's the goal. We want something accessible as those languages, but at the same time have this backend as well. All right, so and to give you an idea of what this can do, we've been running a lot of benchmarks recently. Partly that's to keep us honest and figure out improvement. But also we think we're trying now to really figure this out and convince people that this is really useful and it really does outperform most other tools. And we've picked these problems right now because they seem to be a pretty good spanning set of at least what the customer data-oriented companies are doing. And these should all look familiar, so I'll just keep going. And wanted to sort of also understand how our system stacked up against some other ones. And probably the front runner in single machine tools, at least for performance. Actually, the clear front runner for performance would be relatively small number. Okay, that's interesting. How many people use scikit-learn? Now, okay. What about n different packages for different things? Is that what a lot of people do? liblinear, libsvm, libxx. All right. There were a lot of hands. Some of you that didn't put up a hand, what do you use? I'm curious. What's that? You use Spark, really? Okay. Wow. Okay. I mean, Spark is a good production tool. Just interesting. All right. Well, I guess it's technically not one of these, but okay. So yeah, you can also do exploratory stuff with clusters. Okay. Yeah. All right. And then there's some cluster systems that these are the best known ones. So very quickly, RCV1 is this text classification task. It has 100 topics, and we tune the algorithms to get similar accuracy. And so, we're running on GPUs, and we basically, when you compare with VW is a roofline CPU system. There's various intrinsic C code, intrinsic Intel machine instructions in the code And it's been heavily optimized, and so it does represent what you can do with a Roofline CPU system. But we get about an order of magnitude. That's the gap between what the CPU can do and what a GPU can do. And this is running on a machine where we spend about the same amount of money on the CPU and the GPU. So the cost is, we get that order of magnitude also in cost, assuming we're running this on EC2. These costs and energy, by the way, that were based on comparable EC2 instances, just to be very concrete. And liblinear is an interesting, generally regarded as perhaps the best library for SVM/SGD logistic regression, and it's a little bit slower than VW though. So it's very good algorithmically, not quite as much hardware optimization. But scikit-learn is generally not close to these other algorithms, although sometimes scikit-learn will actually wrap one of these algorithms and then it's the same. But with scikit-learn, it's a much more polymorphic environment. Anyway, all right. So interestingly, against the cluster systems, we're doing perhaps a lot better than you might expect. So here, this is a 72 core system, so like a 18 node system. It actually had 4 core nodes. And we're, in about half the time, we train 100x as many models. This is because Spark doesn't currently support multi-label learning, but we're still faster than, even if they did, they're not going to get faster running 100 models versus 1, so we'd still be competitive. The random forest case is against a recent Spark random forest implementation, and we're again comparable with, what's this? This is 8 nodes. So we're competitive with about an 8-node cluster, but of course with a big advantage in cost and power. And then for a single target regression, which is not a good case for us because there's no parallelism in it, we're still doing better than this bigger cluster. And this is currently a weakness of Spark we discovered. It doesn't, because of the way it implements logistic regression without direct support for mini-batch, although we're giving them credit for solving this problem, they don't really solve it. They actually don't come close to the lift that you get with the single machine learners, because they're basically doing one update per pass over the data set. And to get competitive performance with the prediction pass, you need to make hundreds of thousands. So that's a current weakness. I think there's some interest in making Spark support true SGD, but it's not there right now. So those tasks, by the way, are sort of bad cases for graphics processors, but we're still sort of in there battling away. As we get into more compute-intensive tasks, that's where the GPU-accelerated systems really take off. So on say a 4,000 dimensional clustering of some image data, this is handwriting data, where we're doing faster than a pretty big cluster, and it just continues to sort of go. This is a 1,000-node cluster that's custom built by Yahoo people to solve the latent Dirichlet allocation problem. We have a very good, it turns out, LDA implementation that I'll talk about soon, but we can solve that problem in roughly the same amount of time, but obviously for vastly less resources. And we actually get more accurate results too. But that's partly the result of an algorithmic difference, but about 2 of the orders of magnitude are due to the system design though. And one thing that people ask me is, oh yeah, but we have terabytes of data, so you can't handle that. Well, actually we do. We handle terabytes of data simply by running a big RAID on a single node, passing the data through for about 2 or 3 days through a 4 GPU system, and we get pretty decent convergence on terabytes of Twitter data. If you're talking about Amazon EC2, by the way, you can, I think the default limit is about 40 1 terabyte disks per node. So you can actually build a 40 terabyte RAID, virtual RAID, without even giving them a phone call. And if you give them a phone call, they'll give you more. So you can put a lot of storage very cheaply into the cloud. The downside is you may take a few days to complete that, but you know. And the reality is, unless you have a massive cluster, it's going to take about the same amount of time to process anyway. All right, so a quick summary. We get the expected 10x improvement because we have better speed both for main memory and from ALU performance. Against the cluster systems, we do quite a bit better though, and I'll get into that in a minute. And there's cases that are sort of more memory bound. we're still competitive because we have actually rooflined our system, and a lot of other systems are not really rooflined. And when we have compute-intensive tasks, we're both rooflined and operating on this multi-terabyte piece of hardware, and so then we typically get very massive gains. All right, so we get this somewhere in the range of 10 to 1,000 cost advantages, and similar advantages in power used, energy used, and cost. All right, so, well, in some ways it's easy to do benchmarks, but does it really work in the real world? And so far it has, often better than what you've seen. So, this is a very interesting problem because we just did this also to a summary. We didn't do the experiment. But this was at Microsoft, and they were using an existing single machine tool that's fairly widely used in that part of Microsoft. And we got basically a 120x speed running on this tool. And what that, that brought the time down to the sort of hour range. The student could basically just try this, keep tuning parameters continuously for days. And it's not unusual to be able to get big performance improvements from just trying a lot of things. The feature engineering, if you want to do a lot of feature engineering, you have to have enough time to try all the different combinations. So when you can go fast, when you can go fast and you're not having to queue your jobs, you can get big performance gains. So a nice thing is we found a lot of the time, even though we're solving the problem much faster, we really need to solve it, you can translate that into performance gains by exploration. This is a very interesting one. This was an auction simulator. And here's where we used a very exotic architecture GPU with megabytes of register memory. And between the most recent generations of the NVIDIA processor, they went from 64 registers per thread to 256. At 256, you can put a lot of state into a single thread, into registers, and basically do it. That allows you to get about nearly an order of magnitude speed up over the GPU implementation. It puts you into that hundreds of gigaflops range that normally is reserved for dense computations. So that's pretty interesting. It's sort of, and it might look like a one-off, but we're seeing more and more of these one-offs where you can get this very high performance by using register-based calculation. Yeah. Yeah.
How many nodes CPU you have on there on the CPU?
What was the cluster job that was running before? This one? Oh no. All right. So the first one, this was just a single machine tool. Okay. Yeah. Yeah. Versus a CPU. Ours was 120x faster because a lot of existing CPU code is this exception rather than the rule. The speed up from GPU to CPU plus the suboptimality of that piece of code. All right, and there was an interesting classification job that someone was doing recently. We got it down again. This was a cluster job that. We were in the previous slides comparing against Spark, and some of the actual production systems are not really at the level of Spark. So this also looked like a bad case for us because it's a single label regression, but we still got a good speed up. And most recently, Jeff Wan at Yahoo was doing it was basically maxing out one of the machines we were trying to test our GPU code on. We said, what are you doing? And he was running all these libsvm jobs on vision data, the output of a deep learning classifier, and so we were able to do 1 week's work in about 90 seconds. So that's useful, and it took a lot of the load off the machine as well. All right, so yeah, we see exactly the same kind of speed up, sometimes more so because, again, the real production systems are not necessarily as optimized as the prototypes. So, all right, and some of these are bigger than what we would anticipate based on understanding the hardware. So I'm going to sort of digress for a moment to give my somewhat scientific explanation of why that happens. All right, so once upon a time, again, I was in grad school in Single. Computers were computers and had lights and made noise and stuff, and an instruction was an instruction, right? this is a register addition probably, and this is a main memory access, and we charge the same price for those. Whoops, now there's this, because we have GPUs, if we're able to use register arithmetic, that's effectively a tenth of a picosecond. You have to be able to parallelize, but that's how many of those you can do in a second. This one has not changed in decades. In fact, there's main memory latency is probably because the arrays are bigger and so on. So if this is a truly random access, it's sort of 50 to 100 nanoseconds. So that's actually between 5 and 6, depending on how mean you are. And that, when we design algorithms, we treat both of those as sort of O of 1 as constants. And now, unfortunately, O of 1, that constant, which is already pretty big, so I'm going to use O of 1 to denote the ratio of times for the main memory operation versus the ALU operation. So on that example on the previous slide, it was about 5 orders of magnitude. That's not small, first of all, and it's also growing exponentially. It's even more disturbing because the graphics processors are still managing to double packing more processors into the chip and improving in performance. And actually memory throughput, not latency, been going up as well. So basically this constant factor is growing exponentially. So that's very disturbing. That's surely an argument that we probably should stop thinking that way. So what that means is that when people think that way in design code, it tends to creep further and further from its limits. The other thing that goes wrong is that when you have very big data sets, the heuristics that CPUs have for hiding those latencies start to fail. Again, it's caching. If I have a hash table or a binary tree that won't fit in the 8 megabyte CPU cache, now I'm really in trouble because I'm paying, certainly with hash tables, you'll pay that full memory latency every time. Large binary trees, there's actually no way to order a tree such that you won't get big jumps sometimes when you search it. And linked data structures, because they hide the location of the data, are potentially arbitrarily bad as well. So what we use instead is we use sorting instead of hashing. It's actually faster, much faster in a GPU to sort all of the 2 sets of keys and then just match the adjacent ones and then sort back than using hash tables. The B-tree methods that work for disks also work in memory for removing latencies. And instead of, box and pointer diagrams somewhere in space, if you consciously pack them into an array with a known access order, you can often remove the latencies and get faster throughput. So these are some tricks that we tend to use in the system. All right, so, and we have, right now a fairly generic set of machine learning algorithms. We're gradually adding to them. ICA, I think I should have filled in that slide. We've been debugging it recently, and it's pretty good. I wonder if I can. And we're fairly certain, based on the benchmarks, that the ones in green are the fastest implementation for those algorithms that we know of. And all right, so back to the memory hierarchy again. So as I mentioned, there's this fairly strict pyramidal hierarchy in a CPU. The graphics processors actually have this interesting hourglass with a massive amount of storage at the top. And we're looking for more interesting ways, even perhaps more general ways of exploiting that interesting design. And the one we're most interested in right now, and this is perhaps the most interesting part of this talk from a machine learning perspective, is Gibbs sampling is a classic method for general inference. Very powerful in general, and in certain sense gives you even more information, not just aggregates, but the entire posterior distribution you can sample from. It turns out to be a very good match for graphics processors, and by simply taking existing implementations, we can get big speedups by structuring the data carefully and using the tricks that I described on the previous slide. But even after you do that, you find that a Gibbs sampler version of many algorithms is much slower than a state-of-the-art implementation. So we're interested in that. So this is an algorithmic question now. So why, for instance, if you run a state-of-the-art online mini batch algorithm for LDA, it's a variational Bayes implementation. That seems to be the fastest one right now. You only have to run about 10 passes over a data set, New York Times data set or something like that. Even less if it's a massive Twitter data set. Big data generally requires less iteration because you're able to make more updates. You get similar quality model as you would get with about 1,000 derivatives of that method. So why is that? Well, we think we can make an argument that we're right, because when we make this problem go away, it gets faster. This is a LDA graphical model, which I won't go into excruciating data, but basically, so that you know, this is a prior on a vector of topic weights in a document. The large rectangle is a set of documents that you're generating, and the theta shows the topic distribution within each document. Okay, so it's sort of various weights to different topics. The Z is then a specific in this model you assign a specific topic to each word, and so that's the topic, and then the word itself is given the topic. So you sort of, that's the model for generating the document. The Gibbs sampler basically samples from all of the latent variables inside, you know, in alternating fashion, and somehow it's slow. So why could it be slow? Well, one obvious weakness, if you look at this a little bit, is that this M box here doesn't contain a lot of data. It contains the word values in a single document, maybe a few hundred words. The Z is randomly sampling discretely the topic of each word. So it's this discrete value. Very often there's only one or two topics that are important. So this is alternating between a few topics. When you try to compute, when you try to sample from the theta, it's only got a very few bits of evidence that it can use. This is very sparse data that it has to work with. So it's going to be very noisy. It's going to be a very high variance estimate. And in fact it is. If you look at it in simulation, it's very, very poor. So you have this very high variance around the walk to get this value to its final value. So there's a way of addressing that, which is very general. And just some quick definitions. If we have a distribution of the form P of D, Z, and theta, so there's a joint probability distribution. D is some data. Z are labels that we don't really want to keep, but we need to model them, such as those word topic assignments. And theta are the parameters that we really want to optimize and discover. So in other words, we want to integrate or marginalize over those Z terms using the real distribution of them. But we typically, instead of just sampling from the parameters, we'd actually like to optimize them in practice. So for LDA, the capital theta are the two theta psi parameters that we saw, and then Z is the assignments of words to topics. So a standard sampler actually just samples symmetrically the parameters you care about and the ones that you're going to throw away. But actually, we would like to optimize those theta parameters and just integrate away. Sorry, it should say Z. All right, I'm sorry, I haven't updated this, so it's still going to say X when it should say Z. Anyway, so we have this marginal parameter distribution. That's the one we care about. It's the distribution of our parameters that we're trying to learn. One thing you can do to try to improve that estimate is actually take a power of it. If you take a power of a distribution, it's going to sharpen a lot. It'll keep the same maxima, but it'll be a lot sharper. And when you sample from it, you'll get samples usually near the optima. So you have the same peaks. And it actually corresponds to cooling the distribution. If you think of the posterior as a Gibbs distribution. So probably easy to think about graphically. Basically, if you took your original model and made multiple copies of it, simulate independent Z variables in each simulation, but keep the parameters tied. What that does to the parameter posterior, like if this is your original posterior of parameters, you can see sampling from that's not going to be very good. You'll get sort of mixtures of different modes and a pretty horrible estimate out. But if you cool the distribution, which means powering it, then you're going from that distribution to this one. And if you sample from this distribution, you're almost surely going to be, if you're iteratively sampling, you're going to be confined to one of the optima. Hopefully the main one, but at the very least to one of the secondary ones, but at least your samples will be coherent with each other. So, all right, and I don't think I gave the attribution, but this is called same sampling, and it's a technique originally from Doucet et al., probably underused, because we submitted this paper and only one reviewer knew about it, and we didn't know about it. But yeah, it's actually a very nice method for basically turning Gibbs sampling into a kind of EM optimization. All right, so yeah, and so yeah, we use one extra layer of trickery to avoid explicitly taking the Gibbs samples. Basically, we use Poisson sampling, or now we have binomial sampling, to essentially get the counts of the samples. So they sort of become virtual samples. And so what that does, if you recall, the state-of-the-art methods make 10 passes over the data set. Gibbs sampler would typically take 1,000 passes. Now we're actually using 100 samples instead of one. Each time we take a sample, we do 100. We're actually taking, in effect, the same number of samples, but we're able to do it with only 10 passes over the data set, and within a factor of 3. It's actually about 2.5 of the optimal incremental algorithm. So, and that ends up being about 100x faster than the standard Gibbs sampler, and that makes this algorithm competitive with the Yahoo optimized 1,000-node cluster version. And as people often found with same sampling, also you still are doing a Gibbs sampler though, and it's often more accurate, actually usually more accurate than the online variational Bayes, which is using variational approximation. So that's nice. We get both. We seem to be able to get both the accuracy of Gibbs sampling without the performance hit. All right, and so we're trying to apply this to other domains. Yeah, and we like the fact that it's able to integrate away uninteresting variables, kind of like an EM algorithm. But it also actually sharpens the posterior. It sort of still has some of the qualities of Gibbs sampling. You can run the sampler at different temperatures by taking different numbers of samples in each iteration. So you can heat it up using few samples initially and then cool it down. Or if you actually want to truly sample from the posterior, you can run it cold first, and then warm it up to one sample, and then basically you've quickly converged to the equilibrium distribution, and then you can move around and sample from it. So it's quite versatile for sampling. So we're trying to apply that to some other discrete graphical model problems that we have seen a lot in different applications around campus, both in this one is actually coming from analysis of MOOC data, massive course data. It's a model of the conceptual dependencies in a course, and we want to understand how students navigate through that space using limited observations of their exams. Also in transportation studies and economics, where they actually use complex discrete models to simulate people and kind of learn the latent state from masses of data. So, and we looked at a number of tools, and even if we don't change the algorithmics, we can get typically big gains just by using fully roofline primitives. And here's some results on that, on a particular MOOC graph, where we're, just doing a lot better than those other algorithms. And we want to go a bit further, which I won't get into this, but the goal is then to build a truly customized architecture-based Gibbs sampler that's using, again, the very large amount of register memory to store the sample state while storing the graphical model state in shared memory. All right, so, okay, so second part of the talk, I wanted to talk about, we know how to make algorithms on single nodes much faster. We'd like to scale that up to larger problems. maybe not necessarily larger data sets, because we seem to be doing pretty well on existing data sets, but we like to improve model complexity to get better yields, better performance by running more model degrees of freedom and so on. So yeah, and it's not easy because in the mini batch world, I don't know, logistic regression or something, you're doing a little bit of computation and then a model update. If you want to run distributed, you really ideally want to do that model update as fast as it would happen in the serial version, and that often means many times a second. With traditional distributed computation in a MapReduce framework, you run an entire patch of data and then run the reduce, which often takes many seconds. It involves spilling to disk, and so it's really orders of magnitude away from where you'd like to be. And that's a lot of people have switched to either custom solutions or NPI to solve this problem. We want to take try to do this problem as well as we can, so we use a roofline approach as well. And we tend to focus on Allreduce, which I'll explain why we do that. So an Allreduce anyway is just basically taking the data, vector of data, let's say at each node. Typically it's a local copy of a global model, and we want to compute the sum of all of those vectors and then redistribute across the network. So in other words, we're just really integrating all of the gradients, adding up all the gradients from different pieces of data into a single gradient update of the model. So why specifically do we want to do that in one step? Because there are other solutions to doing that, which involve maybe more chaotic updates. Well, we're trying to use these incremental gradients, and the thing is we want to go pretty much at the full speed of the network. Why is that? Well, let's see. This is a folk theorem, but I can give some weak technical justification that the ideal mini batch size for many algorithms is to use a mini batch of data that's roughly the size of the model. The intuition is when it's smaller than the model and you sort of you take the degrees of freedom of the update, apply them to the model, you get more or less non-interacting effects. Like if you imagine you did one of those gradients and another, as long as the number of degrees of freedom is small, they're sort of injecting into the model space and not interfering with each other. If the mini batch is much bigger than the model degrees of freedom, now you have those different updates. If you imagine you serialize them, many of them are changing the same parameters, and so they're not intuitively equivalent. And in practice, this is a pretty good rule of thumb. If you actually just look at the optimized batch sizes for a lot of algorithms, this tends to be the rule. So what that means is you want to be basically taking and processing updates from each host about as fast as that host can pull the data from wherever it's getting the data. So it's, for us it's often gigabytes per second, which puts you immediately pretty much at the network capacity of, say, a 10 gigabit network. So there's a challenge, right? You want to be able to basically do these Allreduce operations at the full bisection bandwidth of some set of nodes. Yeah. So, all right. Yeah, and I just wanted to say, again, the primary reason right now that we see for doing Allreduce is to make algorithms go faster. The data sets and the model sizes for a lot of problems that I've seen, although people in theory have some massive models that they have to distribute, in practice most of the models don't need distributing. So the main reason for doing parallel computation at all is just to speed things up. But yeah, there are some models, and probably as we move forward and we're able to run more complex models, we will need to run them on clusters because they will get better. Okay, so let's see. Yeah. So an important flavor of Allreduce, though, and one that we can do a lot faster than a complete model update, is a sparse Allreduce. So that's where each node, instead of trying, first of all, you don't have an entire copy of the model on every node. You have a small subset of the model on each node. And then you also pull the values that you need to process the next mini batch from the cloud, effectively, from the global model, and then push the updates to the values that you've changed. So some of you that have looked at GraphLab realize it does that in a greedy fashion. And I guess there's another slide. Where is it? I think I might have hidden it. But anyway, probably just as well. It's a little bit too much detail. So an Allreduce is basically a fully synchronized update of models by a process, not a central server, but a process that's coordinated across the network. So it contrasts with solutions like parameter server solutions, where every worker is allowed to push an update. The aggregator, which has the most coordination constraints, has to somehow process that when it comes, and you have to hope that updates from different uncoordinated nodes don't collide. So that I would call the emergency room model. What we're arguing for, and it's very hard to get that model to actually, you can get it close, but it's very hard to get it to run at the theoretical performance limit. On the other hand, a doctor surgery is the model where you're basically doing a pull. The process, again, it's a distributed process, but it pulls updates from all the nodes when it's ready. And generally for mini batch algorithms, that's fine because the nodes are just trucking through doing updates. And if you say, I need your update now, they just give you the last one. So anyway, so we like that model, and it allows us to get really very close to the performance limits. And I would argue it more than offsets any gains you might get from asynchrony. All right, so yeah, all right, maybe let's see how we go. All right, well, I think we can do this. So we're trying to do a rooflined approach, which means we want to make this primitive go as fast as it can. So that means we have to identify the fundamental limits for bandwidth. How fast can you do an Allreduce? And there's a pretty obvious lower bound, which is every node needs to send all of its data out and get the model back. When it sends the data out, the data's got to be caught somewhere by a different node. And when it gets the aggregate, that data has to originate from somewhere else. So there has to actually be effectively 2D messages for each node, one going out, one coming in. And it turns out with more careful analysis, you can show that's optimal. In fact, there's an n-1 because one of the nodes just does send to self. All right, so I've argued why wouldn't you use a parameter server? Well, the trouble is that the total bandwidth, sorry, I didn't spell it out, but the total bandwidth, total number of messages has to be at least 2 times d. D is the message size, total number of bits, I guess, times the number of workers. So that's all got to go into the network. The speed at which it can get processed in the network is going to be the number or the volume of message traffic divided by the speed of whatever boundary it's got to cross. And so if it's going into 2 servers, you have that, or P servers, it's the n-1 messages. Oh yeah, here it is. It's total message traffic divided by the bandwidth of a single node times the number of nodes. All right. So that's suboptimal because basically these nodes are sending all of their traffic out as fast as they can. You can't possibly catch that with fewer than the number of nodes that you have. So parameter servers generally, take a pretty big hit. The only optimal network, assuming the network's interfaces are the same speed, would require a parameter server of the same size as the original network. But then, you might as well just run in the network, which is what we do. So there's a very similar roofline for networks, which is caused by packet latency. So here the packet size is increasing along the x-axis, but there's a fixed latency for creating packets, which means small packets will have lower throughput because you have to actually pay the cost of creating and sending the packet. It has a relatively small payload, so your actual throughput is a straight line again that tracks the packet size. And we measured this on several networks. There's quite a variable range of that latency, but I forgot to say this, it implies that there's a minimum efficient packet size, which is right here. If your packets are smaller than that size, you start to rapidly lose throughput. So you don't want to go past that point. It is a good idea to be right at that point, though, because the smaller the messages, the more hosts you can reach in each step, and therefore the smaller you've made the network diameter and the fewer iterations you need to complete the operation. All right, so yeah, so an Allreduce is a way to synchronize, aggregate updates, and then rebroadcast them. But for many tasks, we need a sparse version of that. Yeah, so this is, yeah, so sorry, it's a little bit out of order. This is the throughput that we measured on EC2. You can see the efficient packet size is actually bigger than 5 megabytes for that particular network. This is a 10 gigabit node in EC2. Yes, so, and by the way, this is the topology that's used in most cluster systems right now for doing a reduce. Because they're doing kind of disk-based, pretty slow reduces, it's not really too much of a performance penalty. But as soon as you start trying to accelerate, for instance, doing graph algorithms that are very intensive on communication, this method quickly becomes not scalable, because as you have more nodes, you're dividing your data into more pieces. And eventually you hit this packet floor, which is of about 5 megabytes. So those methods don't really scale very far. Okay, let's see. So yeah, so there are though optimal solutions for dense Allreduce. It's good to know about them, and it's also important to know if you experiment with MPI, you have to be careful because you probably don't get the right one by default, but they are configurable. And if you do use the right ones, you're able to get very high throughput. So this was a recent paper by some Baidu people, and they actually achieved a very fast, small fraction of a second update on, I think, about a 40 node cluster using these standard MPI primitives. And this is kind of important because until this one, there had not been a lot of success in scaling up deep learning beyond about 8 nodes. But this paper shows if you do basically effectively an Allreduce, an optimal one, you can actually get up to the point where the overhead of doing the network operation is almost negligible compared to the standard SGD update. So the last thing I will talk about is our work on sparse Allreduce. So here what we were trying to do is build construct an optimal Allreduce, an optimal synchronization primitives for sparse data. And as you see, it's a little bit more complicated than the dense case. And among other reasons, one reason it's kind of complicated is the data itself has this very asymmetric frequency. So some features are much more frequent than others, and they follow a power law. So some people have 10,000 friends, other people have just one friend. So power law data, again, for any attribute that is power law distributed, if you sort of sort that attribute by, let's see, by rank, you get a frequency curve that follows a power law. If it's not on a Mac, you'll see the power law there. All right. Well, so I don't actually need this math anyway. I already defined what an Allreduce is. It's just a vector sum across the nodes and then a distribution. The only difference here is that the vectors, this is just VI, is now a sparse vector. So I only have a small fraction of the features at each node. And not only does each node only want to update some of the values, but it only will request some of the values on the next iteration. This is probably confusing, so let's take a concrete example. Let's suppose I'm doing logistic regression. Actually, it could be that I'm doing a gradient update for on any function, could be SVM, of a piece of data that's linearly multiplied by a feature vector V. So I take my data X multiplied by V and then take some logistic function or something else. So when I'm training a model, I basically want to compute the derivative of this loss function with respect to the model, right? In the sparse case, my vector X is very sparse. And if I work through and do a simple differentiation, I find that the gradient vector is a multiple of the data vector. Is that familiar? It means it's very sparse. It means basically when I pull in a single vector or even a block of data with certain sparse features, and I compute the gradient of the model with respect to those features, I only need to update the model coefficients for those features. It's kind of intuitive, right? If you some model coefficient that's not being even used in the inference of the gradient can't really be updated by that piece of data. So that gives you a concrete case of why, given that V is effectively coming from a distributed model, if I have a really massive massive logistic regression problem with billions of coefficients or trillions of coefficients, nevertheless, when I pull in a mini batch of data, it may only have a few 100,000 features. So all I need is to pull in those features in order to do this calculation here. So it should be obvious also that when I want to do this product, I again only need the V values that correspond to the non-zeros in X. So I want to pull in those feature values, and then I want to push out gradient updates for the same feature values. So hopefully that gives you an idea of why sparse Allreduce has to be sparse first of all, and also why it has to, in general, change the pushed and pulled features at each step. Okay, so here's a quick sketch of an optimal sparse Allreduce, or near optimal sparse Allreduce. And remember, the challenge with these reducers at scale is very often keeping the packet sizes large enough. And that usually means that you don't want to break messages down into very small pieces and send them directly to lots of nodes. You want to do some splitting, but you want to split into pieces that are big enough. Generally, that means you do a fairly low degree split. That also helps with practical efficiency because you don't need as many socket connections. So in this case, we're breaking it into, let's see, 6 pieces eventually, but we're going to do it in 2 rounds. So because splitting into 6 would be inefficient in this example, we first split into groups of 3. So our data is being sort of recursively split down to these 2 sets of 3, and then we do another similar splitting layer down into, now we're splitting pairs and doing it in a butterfly fashion. The end result is we get a single copy of the reduced data, but it's much more efficient now to do this than to try to send all the data to one site, because it turns out we can do the later layers of this process much faster. If you look at the volume here of each message, the volume is also going to be roughly the time it takes to send the message. And the volume is decreasing dramatically as we go down the network. So yeah, hopefully that captures some of the intuition. Now, once we get to these black nodes, we've actually fully reduced the data. So each black node has the sum of data basically from all nodes. Okay, so all right, so we have these heterogeneous degree. In fact, the degree should be decreasing all the way down the network because the packet sizes are decreasing as well. And that will allow us to keep the message size roughly optimal. And all right, so that just tells us that we're not suboptimal because we're using efficient message sizes. But a remarkable thing happens that sort of, I suppose, a bit of gratuitous luck, that we're actually able to still reduce the packet volume because of collisions with power law data. Normally, if you have 2 random uniform sparse vectors and you took the sum, the sum would basically be the size of the sum of the 2 inputs. With power law data, the vectors are packed very densely in the head of the vectors, and so you get a lot of collisions for the most frequent features. And actually, with sparse data, you get significantly less. When you add 2 sparse vectors, the result is significantly shorter than the total length of the 2 vectors. What that means is the network volume as you go down these Kylix networks is decreasing. Now I'll skip over this stuff. And I'm going to go quickly through this, but there's some optimal degree for each layer that keeps the network size reasonably large. And given that, we can actually analytically compute the density of the next layer, which also means the volume at the next layer. Yeah. And what we see in practice is something like this. So this is the total volume of communication at the first layer of one of these networks for a particular Twitter big graphical model. And you can see at the next layer it's reduced by more than a factor of 2. And it continues to reduce all the way down the network. So in fact, the total volume of communication, and given that we're operating at the efficient packet size, this data is actually produced and consumed at full speed. So to get the latency, all we have to do is take the total volume of data that's flying around the network and divide by the individual network bandwidth of each node. And again, that basically puts us within a factor of 2 of optimal. 2 is basically the volume of the total communication relative to the first layer. The first layer is the required communication to send it out and get it back from each node. So that's, for this kind of problem, we're quite happy with that result because it puts us not quite at optimal, but within a small constant factor. It's not obvious at all that you can get anywhere near the, the theoretical limit because we're operating on I think 100, 8 by 4 by 2, a 64 node network, when in fact the packet size already degrades drastically after 8. So so basically we make the big network look like a small one in terms of latency. Okay, so so we did some experiments with Pagerank on both the Twitter followers graph and the Yahoo Web graph that have these structure. And we compared against, Powergraph, which is sort of the, as far as we know, the most high-performance algorithm or system for this problem. Powergraph was implemented pretty efficiently in C code, and generally does quite well for these kind of problems. But we're doing a full, a factor of 5 for one of the problems, and then a factor of about 2 for the other one. And generally, we expect that gap to increase as we scale up to larger networks. Again, the asymptotics are, basically, we're doing a constant factor of optimal in our case, and GraphLab, because it uses an all-to-all reduce, will sort of linearly degrade with larger networks. Okay, so I'm actually at the end. So to summarize the talk, the approach we're taking is to try to use Roofline Design, which means articulating the limits for single machines, memory and CPU limits for or ALU limits for single machines, trying to design all of the kernels in our system as close as we can to those limits, and using, in some cases, sort of knowledge of the hardware to design and tailor the algorithms. So, and the result is that we get one and sometimes several orders of magnitude over other tools. And we also have found that part of the reason is that a lot of other tools haven't been designed consciously with roofline limits in mind, and there's a sort of a slippage that will happen because of the relative inefficiency of common programming practices on big data. So rooflining is a powerful tool and allows you to get close to linear speedups in cluster computing. All right. So we have so the toolkit's available. It's BSD licensed. Because we use a lot of native code that's tricky to compile, we distribute both the GitHub source and then separately a package that includes all the binaries for Windows, Linux, and Mac. And we have some new stuff in the latest release, the random forest implementation that we're quite happy with. This is actually a scalable single node implementation. So it's, as far as I know, unique in the sense that it basically is able to process mini batches of data up to very large size. It doesn't have to pull the data into memory. We added double precision support. We have an iScala notebook, which is similar to IPython, but allows you to use the interpreter in an interactive framework. We're gradually adding some simple deep learning support. There are many other toolkits, but I'm not very convinced. I mean, there's some great toolkits for vision, for image data, namely Berkeley's Caffe, and we're very close to finishing up a wrapper for Caffe, so you can run Caffe from inside of BIDMach. But the support for sparse data and text data, those kind of media with deep learning, I think is not very good right now. And we have some specific designs that we want to try out pretty soon that will, basically fully leverage the sparse primitives and other tools that we've built up in the matrix layer. So, all right, so that's it. So please at least take a look. I think you should try it. I think you should use it. You could probably get, we also really appreciate feedback if you tell us how to make it better or what other things you think we should focus on. We really appreciate that. All right, so and otherwise, yeah, thanks for the invitation, and I'm happy to talk to anyone after. I'll hang around for a while. Thank you.